Welcome back, Precalcsters. Today we are going to start looking at the graphs of sine and cosine, and it's awesome. And I think you guys might have done it a little bit last year, maybe. I have no idea. Way easier, I think, than you imagine it will be. If your name is Sean or Huggins and you're watching this video, next time you walk into class, you need to snap your fingers and give me a high five, and there will be a prize for everybody. I don't know what it will be. Here's the deal. Nobody in here can comment on this to them. We're playing the trust game. If they don't do it, you guys will get... Oh, yeah. We're switching it right now. Hold on. Sean and Huggins, high five me after snapping your fingers, and I will have a reward for you two. If both of you do not, everybody else in the class will get a reward of some sort. Don't know what it is, but this way you guys have no motivation to tell them, right? Also, Huggins is a nerd. Cool. So is Sean. Cool. So are all of you. Awesome. All right. Here's my question for the attendance. We can start organizing this. I don't have notes in front of me. So we're going to look at 7.5 today, and that's where we're... Whoa. Nope. We're in chapter 4. 4.5 is our focus, and we're going to look at graphing sine. No, you don't. Sine and cosine. I have this weird thing where if somebody speaks an untruth, I know it right away. Yeah, that's not in the right spot, but we'll move it. Graphing sine and cosine. I erase this at the end, so this might be annoying for you, but that looks like middle. And then I erase it. That one actually looks pretty middly to me. Doesn't matter. Here's my question for you that I want you to get a little prep for. Somebody said incorrectly that they hate graphing. How many of you guys maybe don't love graphing? Okay, here's my challenge first and foremost. What specifically, not like, oh, I just don't like it. Like, what specifically about it do you dislike or struggle with? And even if somebody feels like they like it, I think you could probably answer this because I'll tell you there's parts of graphing that I don't like. But I'm going to give you like 30 seconds to think about that while I knock out the attendance, and I'll have you guys do another thing here in just a second. What about graphing don't you like? Be specific. Be specific. All right, JV, I've heard lots of words out of your mouth. What don't you like about graphing? It can be time consuming. I agree wholeheartedly. Because you give me any two locations in space, any points, right? And there's how many points between them? Infinitely many. We ain't got time for that. Okay, so I agree. Sometimes it can be awful. Now, I take the approach with graphing stuff that I'm well aware computers and things exist. So sketches are primarily what we do. We're going to be graphing to start today, but then we'll switch over to sketching. Time consuming, I get it. What else? What do you hate about graphing?
It's the fact that, like, the math towards graphing is confusing.
The what?
Like, I think it's function stuff that I absolutely hated.
So
When you had to graph functions.
everything other than a circle that you've ever graphed has been a function. So you've hated every graph you've ever had to make. Can you be more specific other than just saying I hate the fact that we graph?
Wait. I don't know how to explain it though.
Can you draw it? I don't know, whatever you're trying to explain, but you're having trouble coming with words? Okay. Barsega, what do you hate about graphing? Cough drops, get it. Angel, what do you hate?
I'm not really accurate when it comes to hard.
Okay, so there's a lot of attention to detail, which I think it probably comes back to the tedious thing. I do it because I teach it. I hate making tables. I don't mind the graphing part itself. I flippin' hate making tables of stuff, though. Not my thing. Goes back to that whole time-consuming thing. Now, if I asked you to plot points, you could. I think and I hope. Any point that I give you, you could probably roughly plot it. Would you agree with it? Now, all of our points up to this point in time have been x and y, right? And our functions take an x and they spit out a y, and then you just have an ordered pair, right? Now, we are going to think in ordered pairs still, but we're going to make a little shift. And we still haven't even gotten to the part where I'm just going to ask you guys to do a little digging around on the unit circle, but we're getting there. I should probably have notes in front of me, but a little bit of intuition building. We will continue graphing points. And there's a couple ways that we can look at this, but we're just going to change a perspective. Now, it doesn't really change what we're doing other than just how we think about them, okay? So we're still plotting points that have two parts to them. We will graph using, and these are going to be specific ordered pairs. So I'll write ordered pairs. You can just say the word points if you want. Ordered pairs of the form. Now, traditional ordered pairs, they look like what? X and Y. Ours are going to look a little bit different. And I just want to highlight here that traditionally in purple, don't write it right now, this is what they normally look like, right? Now, if we just call it a function instead, is this any different than this? Like it's just plug in the x and whatever it spits out at me is the y value, right? Okay. Ours are still going to be in this flavor. They look a little different, but we're going to start thinking right now as theta and f of theta. So all we're doing is changing x to theta. And why would I possibly do that? What does theta like specifically represent for us? Well, dangle an angle. All right. Here's my challenge for you while I do attendance. You do not have to write this down explicitly, but I do want you to at least somewhere jot down some ideas. It can be in your margin, whatever the case is. Are there nice, and I'm going to put that in quotations, are there nice points around the unit circle which, or that rather, that we could plot? Okay. Now, just to highlight this out real quick, nice is subjective. Totally subjective. I don't really think that the point 0.289536 and some other super ugly decimal, I don't even remember the numbers I used, that's an ugly point in my mind. Do you agree with that? Like super decimally is blech. Okay. Using your unit circles in front of you and, you know, those big old computers inside your brain and the voice boxes, I want you guys to talk out and see, are there nice points around the unit circle? Now, for now, don't look at just the points. I want us to focus on just sign right now. Only for this point, theta, and what's the function that I just said we're going to use? So f is the way that we wrote it here. But if I say we're only talking about the sine is our trig function. This is like my f of x. I want you to work around the unit circle and identify, there's probably some nice points here. I will give you a minute. I will pause it and take attendance. Cool. All right. So, red question here. I'm going to erase in just a minute, but just interested in hearing any nice points that you guys have discovered. Abigail, were you able to find a nice point? Okay, so I love it and hate it simultaneously. Abigail claims that pi halves and 1 is a pretty nice point. Now, 90 degrees feels nicer, right? Because you can think of the number 90. This is 1.7 something. I have no idea what it is. Somewhere in there. But that's kind of nice, right? Can you give me another one? Barsega, what you got? Okay, so pi fourths. Not terrible, and we'll talk about how that's not terrible in a second. But here's my issue. If I asked you to plot the point 1 comma root 2 over 2, where's root 2 over 2? What is that as a number? Do you agree that, like, not super nice? I think it's 0.7, but I could be wrong. So maybe it's nice, but I think root 2 over 2 is kind of rough. Now, again, it's subjective. So, yeah, one could argue it's nice. Any others? Does pi give me a nice point? Well, that's a pretty easy one to graph, I think. What about 3 pi halves? Negative. Hey, that's a nice one as well. What about 2 pi? Okay. One of these things is not like the others, I would argue. And I can even sneak in one more. What's 0? Okay. Now, one of these things is not like the others. Kind of. Can you tell me which one does not belong? Maybe theta 0, but I would claim that 0 radians is still an amount of rotation. But I like where your head's at. Why does this one maybe not belong? Subjectively uglier than the others? Okay. Now, what I want you to do for just a second, we have these values. If I asked you to look at cosines instead, are the theta values, my independent axis, do those give me nice values of cosine that I could possibly use? I think so, right? If we switch to cosine, what's a cosine of 0? It's not 0. It's 1, because you're there, right? 0 degrees, and everybody gets this mixed up. When I talk about cosine of 0, we're not on the x-axis. We're at 0 degrees. We're 0 radians. Okay, what's the cosine of pi halves? How about the cosine of pi? And 3 pi halves? And back to 2 pi. Those are all also super duper nice points. Now, as we look at these, kind of surprised that nobody gave me a pi, if we're looking at sine, kind of surprised nobody gave me a pi thirds, because 1/2 isn't terribly ugly. But on the flip side of that, cosine of pi thirds is ugly. It's root 3 over 2, and the numbers are harder to think about. Now, I'm getting rid of this. You guys can keep it. You do not have to erase yours. But if we can all agree that those points are pretty nice, we get everything that we need. Now, for our first section, we're going to jump right in with it. Let's start with sine. So first main topic, and I'm just going to say graphing, and then we're just going to split this up. So our first little subsection is sine. So we're going to look at graphing a sine function. And what you guys just expressed to me were 5 wonderfully nice points that show up along my unit circle. Now, maybe you call it 4 because 0 and 2 pi are the same, but they were all really nice and easy points to work with. Before we get into graphing this, have you guys, and I'm sure I've asked you before and I'll ask you again, have you guys graphed things that look like this? Have you graphed sine and cosine before? Okay, so if I'm going too fast, let me know. If I'm going too slow, let me know. I have a sweet GIF to show you guys regarding those ideas. There's me. Okay, so I got to turn a bunch of stuff off here real quick. Okay, what? Get out of here. All right, we're going to pause this. Okay, this is super nice. Oh, I won't do it here. There we go. Okay, notice what just happened. If we look at this, and I'm kind of spoiling a little bit here, but that's all right. If I look at sine, because that's the one we're going to focus on first, you guys gave me a bunch of key points. The sine of 0 degrees or radians was what, according to your unit circle? 0 radians. What's the sine? 0. Now, the next nice quote-unquote point that I get to, I think, is pi halves. What's the value of sine at pi halves?
1.
What's the value of my graph there at 1, or at pi halves? Yeah. Yes, you are correct. Sorry, there was like 4 answers there, but I think they were all good. The next nice point that we identified was the sine of pi, we said was
0.
Now, I'm just going to let this thing play. As I look at the circle moving through each quadrant, I can see the y value that it spits out shows up immediately. Okay, this is a single period of sine. And we'll talk about why we call this a period here in a second. But notice how nice and smooth this curve is. If we had wanted to take a totally random point, and I don't know why it doesn't sense it there, but like, let's see, pi fourths is about right here. Root 2 over 2, I'm pretty sure is 0.7 something. Would you guys agree that that y value looks about like 0.7? I think so. Pi thirds, or pi sixths, I'm sorry, is about here. What's the y value of pi sixths on the unit circle for sine? Does that look like it's about that 1/2? So what this boils down to, and we'll come back to this here in a second, is we really and truly are only going to use a few points. We could use infinitely many, but I don't want to, and I don't think you want to. When we're graphing, and realistically it's sine or cosine, we're going to make the first little comment. We need 5, what I'm going to refer to as key points. Now, for these points, you could pick a bunch of random ones if you want. I'm going to give you the ones that I think are always going to work the best. No matter how ugly our sine function is, these points, we'll be able to adjust them to make it as nice as possible. So we're going to take a really brief moment. We're going to construct a little table. Instead of making an XY table, we're going to make a theta sine theta table. And if you want 3 column, you can, but because we're only looking at the unit circle, I don't think we even need that middle column to show our work here. We'll build up to 3 columns eventually, but just real quickly, remind me, what are the angles that give me nice values for sine? 0, I think, started, right? And the next one? So you're backward. Pi halves. And then pi, and 3 pi halves, and 2 pi. I want you guys to go ahead and finish the right side of the table for me. Using your unit circle, find me these values. And I know I commented about how much I hate tables. Hopefully we won't have to use tables for much longer. Cool. I'll give you a minute. When we graph this, do you want to graph it on your page or do you want a sticky note of graph paper? Okay, so yes, will you take one and pass it around? I can probably get another one going on this side too. So I'm just going, so here's 0, right? And the y value is 0. So 0, 0 is my first point. And then pi has 1, pi 0 again. Yep. 0. Yep. What's the y value at? 3 pi half? Try again. What are you pointing at? What's 0? Is that actually y? Good. Yeah, you got it. All right. Now, going through this, I only checked one, but I am hopeful. If you don't know where I'm getting these numbers from, what are you going to do right away? Yeah, shout it from the rooftops, right? Not literally because it's super rainy out and you shouldn't be on the roof. But what's the sign of 0? Okay, what's the sign of pi halves? And okay, first and foremost, do y'all see a pattern? Now, notice, and there's a couple ways we can think about this. We don't have to add a bunch more, but I'm going to write a little bit more that I wouldn't normally do, okay? And you don't have to. What does it seem like I'm jumping by each time? My delta theta, if you will. To get from this to this, what do I have to add? Pi halves. And to get from this to this, what do I add? And this, same thing, right? So if I wanted to extend this table further, what would the next thing be? I know that this is 4 pi halves is the way I would write that. What's the next one? And then 6 pi halves, which is just 3 pi. And 7 pi halves, right? And we could just keep going. How long could we do this for? How long? Forever, right? Okay. Whether you write these ones or not is entirely up to you, but do you think that you could reason a pattern out from the ones that we have and tell me what happens next? 0, 1, 0, -1, 0. It's a good thought. Check for me real quick. You can't see me on the video, but I'm at 0, right? And positive is that way for you guys? So check it out. I'm going to start here and I'm going to go 2 pi. And if I go 1 more pi halves, what's the y value? It's 1. What do you think the next one's going to be? Okay. Is it just repeating itself? Holy periodicity sine function. That is the periodic function that we see happening, and it's just repeating itself over and over. Now, when we make this change, I want you to do me a favor. You guys are going to graph it on that graph paper that went around. You can stick it right in your notes, but we need to agree on a scale, and it doesn't have to be exactly the same necessarily, but I do want to make sure that we can at least see a certain amount. I have no idea how many squares are on that. In this ordered pair that we're looking at as theta and f of theta, which happens to be sine this time, what's the independent, what's the independent or the x in this situation? What are we plugging into the function? So we can think of this as, right now, we have a theta axis instead of an x-axis. So here's theta, and then this is f of theta. And in this case, it's sine, right? Okay. Here's the one part that I want to make sure that we have. When you're doing this, and it depends on how big of a graph you really want, but when I talk about the lattice points of a graph, do you know what I'm talking about? Where the crosses cross. So anywhere that you see 2 lines intersecting is called a lattice point. When you're looking at this, I'm going to eyeball mine, but if I were you, I would make 2 squares. And is that big scale? Yep, I'm okay with that. I would go 2 squares and call it pi halves. Then I would go 2 more and call it pi. And then I'm not even going to label this one because it's going to get ugly, but that's 3 pi halves. And then 2 pi. So all I'm doing here is instead of saying x's, I'm just giving angles, but they are still just going to plug in. Okay. In the other direction, because I already have them labeled, I don't think I really need to, but check it out. I can do the same rough on mine distances, where I know that this would then be negative 2 pi. So I very intentionally made it so that we can see to the right and the left. Equal spaces is super important. If you need another piece of paper, you can take one. What's the only y values that I might possibly need to throw on this? 1 and negative 1. So here's 1, and here's negative 1. Now, the graphing has changed a little tiny bit. Not significantly. What I want you guys to do, and I'm going to catch up to you here in a second, is I want you to plot those 5 points. Just those 5 that we had. I'm going to pause it, and then we're going to come back to this whole period idea. In 3, 2, 1. All right. Here's those 5 points that I had, and that I assume that you have. Some people are still jotting them. But Mickey asked a good question. She said, you want us to draw the graph as well. And she used the word line, and this is the part that I want to really get on with it. These functions are nice. Sine and cosine, they're both super nice. The common mistake in green means don't do it. This is wrong. The common mistake people make is this. This is incorrect. Now, we're only using 5 points, so it seems reasonable that you might try to draw it like this. You do not have to put them, but I know there's other points. I know that at pi fourths, we're about 0.7, which is like there. And I know at pi 6, we're about 1/2, which is here. And I start to see that there's a little bit of curve, even at this scale. Now, when we draw the actual graph of sine, try to make it curve. And then this is always a struggle for me up here on the board. But curve, not pointy. This is what the graph of those 5 points looks like. Nice, smooth curves. Now, it doesn't really skip over anywhere there. I just stopped drawing through pi so I could see it clearly. Now, if I had included those purple points there a second ago, if I just keep ticking, and like if I have another tick here, for example, let's see if we can just work out the pattern without having to evaluate it. 0, 1, 0, negative 1, 0, 1. Do you guys agree that this next point, and I'm changing color specifically, is going to be here. If I went another tick over, where would the next point be? 0, and this is going to look awful for a second. But if I went another tick over, and another one would be back to, and 1 again. Do you guys agree with that? Now, with just those points that I just added, check out what happens. Does it look like the same graph? Okay, when we talk periodicity with these things, this is the easiest possible way to see periodicity. I'm going to copy this whole graph. I'm just going to copy it and paste it. And I suppose I can get rid of these numbers and stuff because it makes it awful. But the periodicity part of this, it's like we can literally just imagine picking up our function and putting it down again. And what I mean by that is if I pick this thing up right now and I put it down here, it wasn't perfect because I didn't graph it perfectly, but do you agree it's the same shape? Where else could I put this? I could put it there, and then could I put it over here again so it does this again? Could I do it this way? And if I let that go forever and ever, it'll just keep waving and waving and waving forever and ever, right? Okay, so couple things. That smallest increment before we start getting everything repeating itself, it had a name. And in this case, what's the distance in the theta direction that we have to move before we get the exact same picture and put it down again? 2 pi. Gosh, what is there's a language for that. This right here, just this red part that we have, this is 1 period of sine. And if you guys check your notes, and you may remember it off the top of your head, this is the period right here. And what is the period equal to for sine? Based on just this picture, whether you remember the other stuff or not. 2 pi. Now, there are so many little things that I can't wait to share with you about how to make these easy and easier than graphs you've done before. The period is 2 pi. Now, if I kept this pattern rolling, and I would just do this with dashes if I were you, but I know that if I work left instead, I'll go down to -1, 0, 1, and 0 again, right? So I see all of a sudden, here's another period of pi is all that I'm seeing. How many periods could I stack together again? Like if I just kept going, my wave would keep waving for how long? Forever. Which means as I'm looking at this, are there any places that I have to pick up my pencil, and you have to, I know that I did here. Are there any places that I have to pick up my pencil to get to the next part of the graph, or does it just keep going? Which means you just answered a question for me that people get goofed up on. If I ask what thetas can I plug in and you tell me all of them, you just gave me the what of sine. The domain. It's the same as saying what x's can I plug into a function that we're just calling x is theta here. So just from this picture and the fact that I know that it keeps going, we know now that the period of sine is 2 pi. What's the domain, DOM, of sine? Somebody said it. I loved the answer. All reals. Now, remember, we have a few ways that we can do this. I'm going to provide all of them. If you like all reals, I'm good with it. Totally good with it. Can somebody give me another way to write all real numbers? Like, I'm not going to write the 3 words. Is this an interval? The real numbers start at negative what? Good. Angel confidently whispers infinity. And they end where? Positive infinity. Cool. The other way is like a blend of these two. Theta such that theta is in this interval, or is a real number. Okay. There's always a third question that's going to get hit here as well. We did the period of it. We did the domain. There's one more. The range. Now, from a graph, it's my hope that the range is super easy. Domain is asking about the inputs, the independent, the x, the theta. What's range asking about? the y, or the output of my function. What's the lowest value you ever see on this graph? -1. Why did I use a bracket? Like, here's a parenthesis here, but a bracket here. How come? So it stops there, kind of. I like the idea. I think you probably have it. Rafa, what'd you say? Yeah, I include this y value, right? I can't include the number infinity. It's not a real number. Okay, so I start at -1, and then I hit every value up until I get to where? Biggest value. 1. Okay, we have worked out the very most basic of this. It is up to you whether you do this on the same graph paper or if you do this on a new sheet. There's plenty more to go around. We just graphed sine here. What I want you to do with your groups for a minute, and this is sine, cool. What else do you think we're going to tackle today? Cosine. Now, for this, there are some things you could possibly do to make this look a little bit nicer in your notes, but I'm fine with just taking it nice and slow, making sure we get it. What I want you to do for cosine is exactly what we just did. I want you to identify using the same angles theta as 0 and pi halves and pi and 3 pi halves and 2 pi. I want you to find the cosine values for each of these angles theta and to again graph it. I want to be able to see 2 periods of cosine once you graph it. This is the first one. This is a standard period that we deal with. I'm going to give you a minute, and as you're doing that, I will get my graph ready. Cool. Talk it out. Ask questions if you have them. So we're going to graph cosine as well, right? And the shape is kind of different when you first look at it, but just hook it up real quick. JV, what's cosine of 0? Good. Charles, cosine of pi halves? Riley, cosine of pi? Barsega, weird. 0. And Kalisha, 2 pi. Now, when you graph these, and notice I don't have fancy graph paper or anything, I get to pick my scale. Cool. The y values only range from 1 to -1, again, which is kind of convenient for us. There's my 1 and -1. Now, when I actually graph these, and when you graph them, here's what I would suggest. I know I'm going to go from 0 radians to 2 pi radians. So all I have to be able to do is say, hey, look, here's pi, and here's 2 pi. Then when I split the difference on each of those, without labeling them, can you tell me what those little dashes that I've added are? Pi halves and 3 pi halves. Now, in doing this, only using these points, I don't care about everything else. There's one huge important distinction that we're going to see. Cosine of 0 starts at 1. So I'm going to make you guys repeat this real quick. Cosine starts where? At 1. Where does sine start? What about cosine? Okay, which one starts at 1? Which one starts at 0? Who's the coolest person you've ever met? Boom, look at it. All right, so we get these points, and I can follow 1, 0, -1. That's off a little bit. 0 and 1. Now, this one looks a little bit different. It's still a nice smooth curve, and all I've done is I've changed the y scale just a little bit. But it goes to there, comes back up, and it stops. Now, same thing is going to wind up happening. We see right now 1 period of cosine, and it has a different shape because of where we've selected our period to run from. So, similarly to before, I see that the period of cosine is also what? Two pi. Now, this one's, again, not going to be perfect, but I'm going to try it, and I'm not even going to worry about taking them off. Does this one fit, like, perfectly right here? No, that's awful. However, if I put it right there, does it connect? And I could do it there. Could I do it here? And all of a sudden, does this also produce a wave that runs forever? So, from that, just by following this pattern, I'm going to really roughly and terribly eyeball this out. I think it does this. There's the second period of this. Okay, same thing. What's the period, one more time, of cosine? So the period, and I'm going to shorthand this, PER is how I do this. The period, 2 pi. What is the domain of cosine, assuming that we let this thing run forever? Good. All reals again. How about the range? Once again, it's the same thing, right? We only get values from -1 to 1. Now, where things get weird, if you guys, I hope you never have, but it's certainly possible. Anybody ever been hooked up to an EKG, an electrocardiogram? You definitely have. Anybody who's had surgery has, whether you've known it or not. If you haven't seen one or don't know what I'm talking about, if I asked you to draw a heartbeat like you'd see on a computer monitor in a hospital, everybody would draw probably something that looks beep, beep, right? Now this is called a sinusoidal rhythm. It sounds really fancy. Sinusoidal. Sinusoidal. Because notice what happens. It looks like a sine function when you graph it. All noise, rhythms, cycles do something like this. And in fact, we'll use this to model a lot of really cool stuff that happens to behave like a wave. Now, if I gave you 2 graphs, and I'm going to hide my screen for just a second. I have 2 graphs on the board that look almost the same. Almost double helixy, right? Cool. One of them is sine, and one of them is cosine. Which is which and why and how do you know? Why would sine be blue? Because it starts at 0. That means cosine is green. Cool. Awesome. Now, here's the hard part about this. You think that if I moved one of these a little bit, you could distinguish between them? You think so? Well, let's try. I'm going to take my cosine and I'm going to move it to the right. I don't know, like pi halves maybe. I've moved cosine to the right pi halves at this point. Can you tell me the difference? So if I ask you now, am I looking at sine or cosine, with the understanding that I can move stuff, can you really tell the difference? Because they're both what? How would you describe the shape you're seeing? A wave. Cool. All right. Now, basic ideas. I assume you guys had seen all this before. Feel okay with this? All right. This is not supposed to be a scary statement. Don't be scared. You might be. We're going to... What? Sure.
No.
Testing your reflexes. Cool. Just so you know, we're going to take a brain break here in just a second, but this is a big comment. We can graph sine and cosine, right? Like, we just did it. We will move to, and this is what's going to happen starting in the next couple days, we will move to graphing things that look as follows. And I'm only going to write one of them because it's the same for sine or cosine. It doesn't matter. They wind up looking the same. We're going to start graphing things that look like this. Can I use x for angles, or do you want me to keep using theta? Okay, don't know that your book will. Your book will pretty commonly use t for an angle instead, just to differentiate. I'm fine with using theta. Okay, we're going to start graphing things that look like the following. Y, or f of theta, if you will, is going to be equal to d plus a sine of b theta minus c. We're moving to here. Now, these things look terrible, and I guarantee 100% I am going to use x instead of theta unintentionally. It's going to happen. It's just so ingrained. I don't want to write the other one with cosine, but can you imagine what it would look like? You don't have to write it. What's the cosine version of this? Cool. Same things, right? Now, to be able to graph these well and any trig function, and we've seen this, we've given ourselves the most basic versions of sine and cosine. Every other sine and cosine function that you ever make is just some change to those. That means when we look up at these top ones that we dealt with, these are the what functions for sine and cosine? The simplest version of them from which every other one can be obtained. Starts with a P. I still can't hear you. Sorry, this fan just kicked on. The parent functions. These are the parent functions of sine and cosine. Everything else is going to come from here. Now, the big part of this, if you can graph the parents, all that we need to know, that's a terrible bracket. All that we need to know about this is what do D, A, B, and C change? That's the big question right now. Because if you can graph sine theta, cos theta, and you know what those four letters do, we can graph any trig function that you ever imagine wanting to graph. Okay, we're going to do a quick brain break, and that went longer than I was expecting. I love this lesson. Just you guys, I like these graphs. All right, here's our brain break.